On to Chapter 4, Applications of Derivatives. So this section is largely devoted to graphing, but there's some other sort of side topics we'll deal with. We'll use derivatives to find extrema of functions, maxes and mins, to graph functions, big time, using both first and second derivative information, find extrema in applied problems, max-min problems, and introduce a little technique that reverses differentiation. And the remainder of Calculus 1 will involve this sort of reversal of differentiation. Chapter 5 deals with something called integration. Section 4.1 is on extreme values of functions on closed intervals. So the plan is in this section to find local and absolute maximums and minimums collectively to find the extrema of a function. So we'll start with some definitions. Let f be a function with domain capital D. Then f has an absolute maximum value on D at point C, an x value, if f of x is less than or equal to f of c for all x in that domain. So that tells you the function doesn't get any bigger than f of c. Now, it might get as big as f of c in some other places, but it doesn't get any bigger than f of c, and it attains the value f of c. That's what an absolute maximum is. It's the highest point on the graph of the function over its domain, if there is such a highest point. And that highest point could be repeated multiple times. The absolute maximum could occur at different input values. An absolute minimum value on domain D at point C, an x value, occurs when f of x is greater than or equal to f of c for all x in C. For all x in domain D. In other words, the function has a minimum value, a least value, f of c, and it doesn't take on any values less than f of c. And that particular value could be attained at multiple points. The function doesn't get lower than this value, and it takes on this value at x equals c, and possibly some other x values. Together, maximum and minimum values are called extreme values of a function. Absolute maxima or minima are sometimes called global maxes and mins. I think the book mentions this word in passing. It's actually a good word you're likely to encounter in some other applied math classes. But absolute max or min, global max or min, really interchangeable. Okay, we're going to look at a picture here in figure 4.2, illustrating how functions may or may not have extrema. A function may or may not have absolute extrema. It's dependent on the function, it's dependent on the domain. So let's look at these four functions. And I'll just repeat the verbiage from the previous slide. Here's a function, y equals x squared, defined on the whole real line. It has a minimum. The minimum, remember that's the function values, that's the y values. So the minimum is 0, y equals 0, and it occurs at x equals 0. So there's the absolute minimum. There is no absolute maximum. There's no largest point. You give me any candidate largest point, I put in a bigger x value, get out a bigger y value. So this is unbounded above. There is no absolute maximum. It's because it's unbounded above. Here's a function, y equals x squared on the domain 0, 2, including the endpoints. And these are all different functions. They're all functions related to the squaring function, but they'll have different domains. So all four of these, strictly speaking, are different functions, different domains, different functions. They're defined by the same formula. They're just defined in different places. So in part B, we've got a function that has an absolute minimum of 0 at x equals 0, and an absolute maximum here at x equals 2 of, what is that value of the function at 2? It's a squaring function, must be 4. So the minimum is 0, the maximum is 4, the absolute minimum and absolute maximum respectively are 0 and 4, and these occur at 0 and at 2. So there's an input and there's an output. There's an X value and there's a Y value. So when we talk about absolute maxes and mins and other relative maxes and mins we'll define shortly, there's kind of two questions. What is the extrema and where does it occur? So we have the absolute maximum occurs at x equals 0, and that, did I say it correctly, absolute minimum at x equals 0, and that minimum is 0, two different zeros. One of them's an x value, one of them's a y value. The absolute maximum occurs at x equals 2 and is y equals 4, or f of 2 equals 4. Over here, got a squaring function, but this time the domain has been restricted from 0 to 2, excluding the 0, including the 2. A half open interval, as this book defines it. This has an absolute maximum of 4 at 2, just like the previous one, but it has no absolute minimum. Okay, now this illustrates some of the subtlety of this stuff. There's no absolute minimum because there's not a value that the function attains on its domain that's smaller than all the others. You don't get 0 out of this function on this domain. You can't plug 0 in because 0 is not in the domain of this function. That's how the function's defined. So true, all of the function values are greater than 0, or if you like, greater than or equal to 0, but they never equal 0, so strictly greater than 0. There's not a minimum value for this function. For the same reason, there's not a smallest positive number. You give me a candidate smallest positive number, I multiply by half and give you a smaller positive number. Your number wasn't the smallest positive number after all. So there's no smallest positive number. The function values that come out of this involve small positive numbers when x is near 0 and greater than 0. But this function does not attain the value 0, even though that's a lower bound on the range of this function. The range is the open interval from 0 to 4. Finding ranges is hard unless you have graphs. Well, we got a graph. So no absolute minimum value on this one. Here's one that has neither an absolute max nor an absolute min. Yeah, they poked holes in the ends of it. And as we just discussed, there's no absolute minimum. It's like picking the smallest positive number. Here, there's no absolute maximum. I mean, 4 is an upper bound of the function values, but the function doesn't take on the value 4. It gets arbitrarily close to the value 4, and we could say something about a one-sided limit related to 4. But the function has neither a max nor a min. It, I don't know, to go anthropomorphic on you, it wanted to have a minimum of 0 and a maximum of 4, just like in part B. But they poked holes in it and wouldn't let it. So it's related to, must be related somehow to limits or continuity. Well, that's why it's in calculus. So no absolute maximum. Looks like that can occur in two different ways if I compare part A and part D. This one doesn't have an absolute maximum. It kind of wanted to, but you wouldn't let it. You poked a hole in it. This one has no absolute maximum because it gets bigger and bigger without bound. The output values are unbounded over here. Well, they ain't unbounded over here, but there's not a biggest one. For the same reason, there's not a smallest positive number. There's not a biggest value in the range of this function. The range of this function is 0 to 4, the open interval from 0 to 4. And there's not a biggest number in the open interval from 0 to 4. You threw 4 out, the open interval. I include 4, sure, that's the biggest, but 4 is not included as an output. Okay, so what we want to do is figure out when, first off, when a function has absolute maxes and absolute mins. And secondly, where are they? We want a technique to find them, and we'll have a technique and it'll involve derivatives. And we sort of foreshadowed this in some of the stuff we've done earlier. The next result gives a condition under which a function has extrema on a set of real numbers. The sets of real numbers are usually they're intervals, or maybe the whole real number line, but usually the sets of real numbers are intervals we deal with. Proof of the result is beyond the scope of this course. How was it worded? Is involved and requires deep ideas. It's the kind of thing we do in a senior level analysis class. I've got notes posted for senior level analysis. Click on this link in the online notes and it'll take you to notes concerning the extreme value theorem. A proof will depend on the axiom of completeness, and that's discussed in Appendix A6, I think it is, in the Calculus 1 notes. But we got enough problems. Let's just state and take as given the extreme value theorem for continuous functions. So continuous, continuity. We had some continuity in what was drawn in those 4 functions upstairs. Actually, let's look at those again. Yeah, each of these are continuous functions on their domain. I have to be careful, they're continuous functions on their domain. This is continuous. It's got holes poked in the end, but yeah, it's continuous at all points of the domain, strictly between 0 and 2. So all these are continuous functions. So there must be more to it than just continuity. There is. All right, statement of the extreme value theorem is, if f is continuous at every point of a closed and bounded interval, I equals closed and bounded interval from A to B, then f assumes both an absolute maximum value, capital M, and an absolute value, an absolute minimum value, lowercase m, somewhere in I. More specifically, more math symboly, which is more useful, turns out. That is, there's numbers x1 and x2 in this interval from A to B, where f of x sub 1 equals lowercase m, and f of x sub 2 equals capital M. And for every x in this interval, lowercase m is less than or equal to f of x is less than or equal to capital M. In other words, this is a lower bound, this is an upper bound, and the function attains those bounds. It attains this lower bound at x sub 1. It attains this upper bound at x sub 2. That's what the x sub 1 and x sub 2s they gave us mean. So the function never gets bigger than capital M. It never gets lower than lowercase m. And it actually does take on those extreme values. Now, what's not said is that, it only takes these values on once. I don't know. It depends on the function. It says it takes on this value capital M at least once. It takes it on at x sub 2 and possibly some other places. Same thing for the lowercase m. So the new thing here is closed and bounded interval. So we've got continuous functions on closed and bounded intervals. Up here, this is the only time we had these functions defined on a closed and bounded interval. A closed and bounded interval from 0 to 2. Here we excluded the left-hand endpoint. Here we excluded the left and the right-hand endpoints. Here there aren't any endpoints. It's not bounded. So this is the only time that the extreme value theorem applies. And notice the extreme value theorem guaranteed us the existence of an absolute maximum and an absolute minimum, and you had both of those in figure 4.2, part B. So let's look at some pictures, basically. Let's do a couple of examples, which is going to really just involve looking at pictures, looking at graphs. And the question is, determine from the graph whether f has any absolute extreme values on the interval from A to B. All right, there's a graph of the function. That's a continuous function, ain't it? By, I don't know, and Dr. Bob's anthropomorphic idea of limits and the definition of continuity. The fact you can draw without picking up your pencil, I'm happy enough with that. What kind of interval are we on? Looks like the domain of this function runs over the closed and bounded interval, AB, as given. So continuous function on a closed and bounded interval? Yeah. Extreme value theorem says it's going to have a max and it's going to have a min. So f is continuous on an interval of the form AB, including the endpoints. So extreme value theorem for continuous functions says there's both an absolute max and a min. Where are they? Here's the minimum value. It's f of b, because the function never goes below that. And here's the maximum value. It's what you get by plugging in C. It's f of C. So the absolute maximum is f of C. The absolute minimum is f of B. Function never goes below this level, this f of B level, and never goes above this level, the f of C level. Easy enough. Extreme value theorem applied. If they gave us an equation for this function, I'd be wondering how to figure out where that extremum occurs. Any ideas? Let's see. What have we talked at length about lately? Derivatives, and the title of the chapter is Applications of Derivatives. What's happening at this extreme value? Well, there's a horizontal tangent function. I'm sorry, horizontal tangent line. I know how to find that because we've done a number of problems where they had us look for where a function had a horizontal tangent line. And the reason they did it was leading into these ideas here. Let's look at number 4. Here's a function. H is defined on the interval AB, a closed and bounded interval. So far, so good. Actually, it's not defined on a closed and bounded interval. The statement of the exercise is something like this. So that's where I got that. Let's pick this one apart. No, it's not defined on the closed and bounded interval from A, B, because it's not defined at A and B. They put the little open circles there. It's not defined at A, it's not defined at B, it's defined at C. H of C is whatever y value we get out at this point. So it is defined at C, but it ain't continuous at C. So extreme value theorem apply? No, it's not defined on the right kind of interval. It's defined on the open interval from A to B, and it's not continuous. So it's got 2 strikes. Theorem 4.1 doesn't apply. The extreme value theorem doesn't apply. Does this curve have a max or a min? An absolute maximum or an absolute minimum? No. It kind of wants whatever y value of this point we have. We could find that y value with a one-sided limit. But it doesn't actually take on that value. They poked a hole in it to avoid it taking on that largest value. Same thing over here. It kind of wants to think it anthropomorphically again, which means I'm thinking about limits. It wants to take on the y value, the y coordinate of this point here. But it doesn't because they poked a hole in it and they made it take on some other y value. So it has neither a max nor a min. Granted, it's always below this level, it's always above this level, but it never takes on the y value corresponding to this level, and it never takes on the y value corresponding to this level. It has neither a max nor a min, neither an absolute maximum nor an absolute minimum. We'll actually talk about that a little bit more. So the extrema are really the biggest and the smallest, maybe I should say the greatest and the least value that a function takes on an interval. And in this case, there's not a greatest value. Now, if we'll look at the limit as x approaches a from the positive side, that would be, let's see, we'll come in from this side, it's going to try to contain that point. That limit would be whatever the corresponding y value is. But it's not a function value, it's a limit value. But that would be an upper bound on the values of the function. The function's always below this upper bound, and I can write it symbolically. I got to write it in terms of a limit, though. How about the lower bound? Well, that'd be look, it's trying to pass through that point. So if we were to consider the limit as x approaches c, the two-sided limit this time, because we're dealing with an interior point of the domain, the two-sided limit exists, and that would be the y coordinate of this point the graph of the function's trying to pass through. So take you back to the very early stuff when we did limits, back to section 2.1. Now, it doesn't attain either of these values. It gets arbitrarily close to both of these values. You can make the function values arbitrarily close to that limit value by making x sufficiently close to a and greater than a. It was a one-sided limit type deal. We can make the function arbitrarily close to that lower bound, whatever the y-coordinate of this point is, by making x sufficiently close to c. Back to my informal conversations about arbitrarily close and sufficiently close, which turned into epsilons and deltas. But there's no maximum and minimum value attained by the function. It doesn't take on this minimum value or this lower bound, and it doesn't take on this upper bound. The function doesn't have a max or a min. It's related to that idea of a least positive real number. There's not one. You give me a candidate, I cut it in half, and I get a lesser positive number. There's not a greatest negative real number either. You give me a candidate, I cut it in half, and I get one greater as well. Cut it in half, I get one greater. We're dealing with negatives in this conversation. So anyhow, not a biggest value, not a smallest value, not an absolute max or an absolute min. Well, I'm not surprised. It's not a continuous function on a closed and bounded interval. So you see why closed and bounded intervals are needed, and you see why continuity is needed. If this function were continuous, and this point actually plugged up that hole, it'd have a minimum. Now, it still wouldn't have a maximum if I leave it defined otherwise the same. But if we were to extend it to a continuous function on the open interval from A to B, in this case, it would have a minimum, but not as they gave it to us. Back to the notes. Okay, we're gonna back off of absolute extrema and start talking about local extrema. Let C be an interior point of the domain. Endpoints will play a role as well, but let's take care of interior points first. Let C be an interior point of the domain of a function f. F of C is a local maximum value if f of C is less than, if f of x is less than or equal to f of C for all x in some open interval containing C. You know, when they talk like that, they mean close to C. So close to C, we get function values that are less than or equal to f of C. So nearby, the function doesn't get any bigger than its value at f of C, doesn't get any greater than its value at f of C. Maybe elsewhere, it gets bigger, greater than f of C, but in some open interval containing C, the function is always less than or equal to f of C. So it doesn't get bigger than f of C nearby. Maybe elsewhere it gets bigger. Local minimum, if on some open interval we have that inequality reversed. So now we've got for all x values in an open interval containing C, f of x is greater than or equal to f of C. So the function doesn't get strictly less than f of C, nearby, near C. That's what the open interval stuff gives you. Think of it in terms of elevations. You could have a little hilltop that corresponds to a local maximum, but there's bigger mountains out there. You could have a minimum of elevation at in a valley, say, but there's lower valleys out there, or maybe even your valleys above sea level. So this is a local property. It's what we learn about the function nearby. It's close to C. This is some sort of close to C behavior, as you can tell when they talk about open intervals containing C. Again, notice the except possibly C stuff isn't relevant to this conversation. We're talking limits in some sense, but more than that. We've got continuous functions, it must be. Well, I take that back. We've got functions defined on open intervals. The type of question we're dealing with here, there's no except possibly C stuff going on here. These local extrema sometimes are called relative extrema in contrast to absolute extrema. I really like the words local versus global. Local and global are common terms to use here. So are absolute and relative. Here's a picture. Quite apparently the book's gone for local and absolute, so they've sort of mixed those up. But whatever, we're going to see this picture again in an upcoming section. And here's her story. Here we've got a local maximum. The function doesn't go above this level nearby. Now it goes above this level somewhere else. That's why it's a local maximum and not a global maximum. Here we've got a local minimum. The function doesn't go below this level nearby, but it does somewhere else. Here we've got a local maximum. Actually, here we've got an absolute maximum because the function doesn't go above this. It's a local maximum as well, but it doesn't go above this value anywhere else because they've given us a whole picture of the function defined from A to B is what they've given us. So this must be the absolute maximum. It's also a local maximum, also a local maximum. Now at the endpoints, we didn't formally define these. I'm going to depend on this picture. The book goes into even more detail about this, but this is a local minimum because nearby where the function's defined, which is only to the left because this is a right endpoint of the domain, the function doesn't go below this value nearby in the domain of the function. Now it gets lower than that somewhere else, but it's a local minimum. Over here, same story. It's a local minimum because nearby, that would be x values greater than or equal to a, because this is a left-hand endpoint of the domain. The function doesn't go below this nearby. So it's a local minimum. Now, what I'd do if I were me, which I am, is find all of these little local extrema and then just pick the biggest one. The biggest one, the greatest one, will be the absolute maximum, and the least one will be the absolute minimum. So we get we've got 1, 2, 3, 4, we got 5 local extrema and 2 absolute extrema, absolute max, absolute min. And notice what happens, they're really foreshadowing this. The derivative is 0 at these two because it's got horizontal tangent lines because the function went up and it leveled off and then it went back down. Here it went down, it leveled off and it went back up. Here, what's up with that? It's got a corner is what this book calls a point like that. The derivative is undefined there. It's got a sharp point, a corner is what the book calls it. It's got a corner there. So the derivative is not defined there. So I can't draw a little tangent line and see what's happening there. And they put this one in for a very specific reason. At the endpoints, they're endpoints. And I could talk about one-sided derivatives, but it turns out there's no information in the one-sided derivatives at the endpoints. It's the fact they're endpoints that matter. Okay, so now we'll state and prove a result that tells us where to look for local extrema of a differentiable function. So if I could find these local extrema, then I could just pick the greatest one and the least one, and that would also give me the absolute extrema. And that picture is meant to foreshadow Theorem 4.2, local extreme values. And it says, if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C equals 0. So the local maxes and mins occur where the derivative is 0 if the derivative is defined. Let's look back at the picture we just had. We had interior points of the domain, it says, which means exclude the endpoints. We had a local maximum here, and the derivative is 0. We had a local minimum here, and the derivative is 0. Turns out we had a maximum here, and the derivative wasn't defined. Well, it didn't deal with that. The extreme, what was it, local extreme theorem, local extreme values result has hypotheses of differentiability. But it looks like some interesting stuff in connection with extrema can also occur where the derivative is undefined. More of that shortly. Let's go through a proof of this. It's not too bad. Local extreme values. So we want to show, actually we'll go through a proof for local maximum, proof for local minimum would be quite similar. Suppose f has a local maximum value at x equals c. We're going to show f prime of c equals 0. Local minimum value, we'll talk about it very briefly. It's practically the same computation. Okay, so if f has a local maximum at x equals c, that means f of x minus f of c is less than or equal to 0. F of c is bigger than f of x, at least in some open interval containing c. So that's what local maximum means. If you like, move the f of c to the other side, and we get f of x is less than or equal to positive f of c. I want to write this because f of x minus f of c is going to pop up in a limit. So that's the reason it's written that way. But that's the definition of local maximum. Since c is an interior point of the domain, then f prime of c, which is hypothesized to exist, f prime exists at c, is given by definition of derivative at an interior point. At endpoints, we took one-sided limits, but we've got an interior point by hypothesis here. There's a hypothesis right there. We'll use a definition of derivative, actually the alternative definition of derivative. We've used this one a bunch of times. It's presented in exercise 3.2.24. So the supplements to section 3.2 contain this exercise. So here's an alternate way to define f prime of c, limit as x approaches c, of f of x minus f of c over x minus c. So there's some sort of difference quotient we're taking a limit of. All right, so there's f prime of c. We know f prime exists at c. We know this limit exists. Hypotheses. Well, what we're going to do is break it into one-sided limits. Consider the one-sided limits. Limit as x approaches c from the positive side, as well as the limit as x approaches c from the negative side. It's a little crowded at the bottom here. Well, here's what's happening. If f of c is a local maximum, like we have in the picture here, can't magnify these because of the nature of the PDF file here. We got a maximum, so the blue path represents the function, and it's got a local maximum here. If we take a limit as x approaches c from the positive side, what's up with the sign of this difference quotient? X approaches c from the positive side. That means x is close to c and a little bit bigger than c. So x minus c is a little positive number. X minus c will be positive in this type of limit. So the denominator is positive. What's up with the numerator? Do you know the sign of f of x minus f of c? I do. It's negative. So we had the numerator is negative. Well, I'm sorry, non-positive. The numerator is non-positive. And the denominator is positive. So the numerator is negative or 0. The denominator is positive. We're not dividing by 0. It's a limit. X doesn't equal c when I write the limit stuff, as always. And what we get then is a negative divided by a positive. That gives us a negative. Okay, I lie a little bit. It gives us a non-positive divided by a positive, which yields a non-positive. That gives us a less than or equal to 0 out of this limit. Because in this case, we went to the right a little bit, to the positive side of c, and we're going to have function values go down. We'll have the f of x minus f of c be less than or equal to 0 when we go to this side. We'll have similar behavior when we go to that side. That's what the image here is illustrating. How about the limit as x approaches c from the negative side? Well, f of x minus f of c, we still got that being non-positive, less than or equal to 0. This time, though, x minus c, this time x minus c is negative. We're looking at x approaching c from the negative side, so it's over here somewhere. So when we take x minus c, c is to the right of x minus c will be negative. We've got a non-positive divided by a negative yields a non-positive. So from one-sided limit, we get less than or equal to 0. From the other one-sided limit, we get a limit which we know exists by hypothesis to be greater than or equal to 0. All right. Those one-sided limits, they ought to be the same, though, because the two-sided limit exists. because the two-sided limit is the derivative, and they told us f prime exists at c. So the two-sided limit should exist. It should equal this, and it should equal that. It should equal the two one-sided limits. But wait, this one's less than or equal to 0, and that one's greater than or equal to 0, and I need them to be the same. How can they be the same if one's less than or equal to 0 and the other one's greater than or equal to 0? One choice, 0. They must both equal 0, and that must be the value of f prime. That is, f prime of c equals 0. A little bit more on that. Next slide. The two-sided limit exists by hypothesis, the fact that f prime exists at c. So the one-sided limits must both exist and be the same. The only way they could be the same, since one is less than or equal to 0, the other is greater than or equal to 0, is if the common value for all three of these limits, left, right, and two-sided, are all 0. So we get f prime equals 0, and that's what we needed to show. We did that under the assumption that f had a local maximum at x equals c. Well, if f has a local minimum at x equals c, this inequality is reversed. The reversals of the inequalities cascade through the one-sided limits, and you still draw the same conclusion. You get a greater than or equal to 0 and a less than or equal to 0, like we just did. They're just in different places. On the one-sided limits, they'll be reversed. But you'll still draw a conclusion that f prime of c equals 0. So there's the extreme value theorem telling us that there exist, under certain conditions, absolute maxes and mins. The local extreme values theorem tells us where to look for them. Now, the local extreme values theorem, it only spoke of places where the derivative is 0 directly, but it's indirectly telling us other information. So what we get from this theorem 4.2, the local extreme values theorem, is for function f with a domain D, which is an interval or a union of intervals. This we're unlikely to deal with, but it's true. The local extreme values occur at interior points where the derivative is 0. That's what the theorem said. Or interior points where f prime is undefined. It assumed that f is differentiable at c. It didn't say what happens if f is not differentiable at c. Well, I guess we could have extreme values there as well. You could not as well. Or the endpoints, because nothing's been said about the endpoints. So what this rather important note tells you is, here's where the local extreme values occur. They occur where the derivative is 0, where the derivative is undefined, or at endpoints of the domain. Assuming the domain's an interval, and it'll almost always be for us. Probably always. So we just need to deal with the derivative. Happy to see derivative brought up in the conversation because we're so good at taking derivatives at this stage. And it's a matter of setting the derivative equal to 0 or seeing where it's undefined at points in the domain of the function. Oh, and checking those points as well as the endpoints of the domain, if relevant. The two types of points concerning f prime being either 0 or undefined are so special, they get a name. They're called critical points. A point in the domain of a function f at which f prime is 0 or f prime does not exist is called a critical point of the function. I should emphasize, the function is defined at a critical point. It's a point in the domain. So the function is defined there, and the derivative is either 0 or maybe the derivative's not defined there. That's what a critical point is. If the function isn't defined at a point, then the derivative ain't going to be defined at the point. So the order in which these words are laid out is rather important. We're talking about points in the domain of the function, first off. Then we're calling them critical points if the derivative is 0 or if the derivative does not exist. I didn't say look where the derivative is undefined, because there's probably or possibly there's a bunch of places where the derivative is undefined, and it's undefined because the function isn't defined. Well, I don't care what happens when the function isn't defined. I care about what happens on the domain of the function. So, to find the extrema on a closed and bounded interval, here's what you do. First off, if we've got a closed and bounded interval and a continuous function, then the extreme value theorem says it's got maxes and mins. The Theorem 4.2, the local extreme values theorem, that one's not as universally used as the extreme value theorem is. That's why I forget the name of it sometimes. To find these extrema, all we have to do is find the critical points, evaluate f, check the value of f at the critical points and the endpoints. That'll give us the absolute max and the min. Just take the largest and the greatest and the least of these values, and that will give you the absolute maximum and absolute minimum, respectively. So, long story short, we got it down to 3 steps. And as long as we have continuous functions on closed and bounded intervals, and we're looking for absolute extrema, you follow these 3 steps. So let's illustrate it with several examples. This observation here has made it very mechanical. No reason you shouldn't do well with this stuff. It involves critical points, which means it involves derivatives, and you're good at taking derivatives, and then some algebraic manipulations. As long as the numbers aren't too wild, that shouldn't be bad. Number 24, find the absolute maximum and minimum values of the function f of x equals 4 minus x cubed on the closed and bounded interval, -2 to 1. Then graph it and identify the extrema. Okay. Let's follow the 3 steps. By the way, continuous function, it's a polynomial. Polynomials are continuous. So it's a continuous function on a closed and bounded interval. Excellent. The extreme value theorem says it has an absolute maximum and it has an absolute minimum. Before we start looking for these things, we need to make sure they exist. We're good. If they looked at an open interval instead of a closed interval, we might have problems. So we're good. The extreme value theorem applies, and we're good to go to use the 3 steps we just mentioned, which were step 1, find the critical points. We've got f of x is 4 minus x cubed, so the derivative, f prime of x, is -3x squared. Easy enough to take the derivatives. I got some good news for you. The functions we differentiate in chapter 4, they probably won't be quite as complicated as those we differentiated in chapter 3, because we're going to have to actually manipulate them and do stuff with them, so they can't be too outrageously complicated. This one's easy. It's a polynomial. So there's what we get for the derivative. We want to see what the critical points are. That is where the derivative is 0 and where it's undefined. Well, it equals 0 when x equals 0. X is the only critical point, of course. -3x squared is never undefined. So there's only one kind of critical point, and there's only one critical point, and it's x equals 0 where the derivative is 0. Keep that in mind. The derivative is 0 at x equals 0. They want us to graph this thing. All right, at x equals 0, it'll have a horizontal tangent line. So keep that in mind. There's a lot of information in the derivative when it comes time to graph, and it's coming time to graph. For step 2, we wanted to consider the value of the function f of x at x equals the endpoints, -2 and 1, and at the critical point 0. Let's list them in order. -2 is less than, 0 is less than 1, so let's list them in order just for sanity's sake. Plug those numbers into the function, the original function, the f function, the 4 minus stuff cubed function, and we get -2, we get 4 minus -2 cubed, we get out 12, we get out 4 at 0, and we get out 3 at 1. We know the absolute maximum is the largest of these function values, and the absolute minimum is the least of these function values. So 12 is the biggest, the largest, the greatest. 3 is the least, that's the absolute max, and 3 is the absolute minimum. Absolute maximum is 12, and occurs at x equals 2. The absolute minimum is 3 and occurs at x equals 1. I won't give my answers as to what and where in connection with these extrema. Later on, we'll be graphing. Actually, it wants to graph this one, so let's do that. We got 3 points already, -2, 12, 0, 4, and 1, 3. So let's plot those 3 points. And you remember how that derivative behaved. There's information in the derivative. If we plot the points, we get this blue point, and this blue point. What was up? What was up at 0? Oh, the derivative was 0. That means horizontal tangent line. So, some good stuff's about to happen. This function must have gone from this big value of 12 and went down, leveled off, passed through this point. I know it passes through that point. Must have leveled off because the derivative is 0 there. It has a horizontal tangent line is what I'm trying to say. And then it continued to decrease downward to this point. The graph of that function, it must look a lot like this on the interval -2 to 1. So I bet you the graph looks a lot like that. How do you know it doesn't wiggle more? How do you know it doesn't go down and then go back up and then go back down and level off? How do you know it doesn't wiggle more like that? Well, if it did, it'd have more horizontal tangent lines, and the derivative would have told me all about it. So it can't wiggle anymore, or it'd have more critical points, and it doesn't. It's only got 1. So it must just go down, level off, and continue to go down. How do you know it doesn't go through there and start going upward? Well, it's got to get over here to this point. So if it went upward, it'd have to turn around and go back down, which would mean a horizontal tangent line if it's differentiable. Mean a corner if it's not differentiable. Of course, it's differentiable. It's a polynomial. The graph has to look a lot like this. So this is the first time we've pasted together information about the derivative in connection with a graph. I'm pretty confident the graph looks a lot like that because I know stuff about the points on the curve. Plotting points, awful way to graph something, unless they're special points and you know why they're special. We plotted 3 points. We plotted 3 special points. What makes this one special? Endpoint. What makes that one special? Endpoint. I guess in connection with their question, what makes them special is this is where the minimum, the absolute minimum, and this is where the absolute maximum occurs. And this one was special as well because it was a critical point. So we plotted the 3 points. They were special, and we knew why they were special. Critical points, endpoints. That's how we'll use derivative and eventually second derivative information to get really good graphs of functions. Are you good at graphing functions? Meh. Some certain ones you are. You're good at graphing trig functions. You're good at graphing lines. You're good at graphing quadratics. Parabolas is what you get. And maybe a few other things, maybe logs and exponentials. But graphing functions in general, nothing personal. You just ain't that good at it yet. But you're going to be when I get done with you because you're going to use calculus. And you don't plot functions by willy-nilly plotting points. Hopefully you've been told this in the past. You plot functions by maybe plotting special points and using information about why they're special. At least that's the story I want to tell in calculus. Let's do another one. Okay, so it's a section or 2, maybe 3 down the road that we'll get deeply into the graphing, but one of the main applications of differentiation is to graphing. You'll be as good as anybody else at graphing after calculus 1. Question 44 says, find the absolute maximum and minimum values of h of theta equals 3 theta to the 2/3 on the interval -27 to 8. All right, continuous function, 3 times theta to the 2/3. I think so. It's power of theta. It's continuous. Is it defined everywhere? We got any square roots and negatives or anything? I hope not, because there's some negatives that they're interested in. No, it's a squaring and a cube root. And you can take cube roots and negatives. So we're good. This function has as its domain all real numbers. It's a continuous function. It's just the power of theta. We possibly looked at graphs of these in the past. So let's apply the 3 steps. It will have an absolute maximum and minimum. It's a continuous function on a closed and bounded interval. Extreme value theorem said so. So the 3 steps, we'll take a derivative, piece of cake, bring the exponent down, subtract 1 from the exponent, produces this. Let's see, have I dropped a 3? I believe I dropped a 3. There's a boo-boo here. I should have a 3 out front. The 3's would cancel and I shouldn't have a 3 here. I will correct the notes. Another typo. That's not going to affect the following computations, but this is incorrect. I need a 3 out front and then a 3 out here, or cancel with that 3 if you like. I will update the notes. But we get the derivative to be, I'll just cover it up for a second. We get 2 over the cube root of theta. We got a theta to the negative 1/3. How about I write that as a cube root of theta in the denominator? So we get 2 over the cube root of theta. All right. Is that 0 anywhere? The only place it could be 0 is where the numerator is 0. The numerator is not 0. It's too busy being 2. So the derivative is never 0. Is a derivative ever undefined? Yeah, I can't divide by 0. So when theta equals 0, we would have division by 0. The derivative is undefined at 0. Is 0 in the domain of the function? You know what 0 to the 2/3 power is? It's 0. Yeah, so 0 is in fact in the domain of the function. So barring the little typo there, I stand by my claims that the derivative is never 0, and theta equals 0 is a critical point because the derivative is undefined there. What's that tell you about the graph? It ain't nice and smooth. If it was nice and smooth, we wouldn't have this undefined derivative. More of this in another example. They didn't have us graphing this time. They just had us finding extrema. But we'll do one shortly where we look at some oddball behavior concerning critical points where the derivative is undefined. All right, so theta equals 0 is the only critical point we have. So we need to check, according to our 3-step method, the value of h at the endpoints and at the critical point 0. So for step 2, we'll make a table again, get used to making tables because we're going to do lots of that in chapter 4. Endpoint, critical point, endpoint. We'll plug those into the original function. I want the, these are theta values, and I want h of theta. We'll copy and paste, boo-boo there. I want to plug the values in here. So I'll take the negative 27, plug it in here. We get 3, negative 27 to the 2/3 power. The third means take the cube root. So cube root of negative 27 is negative 3. Square it would give us positive 9 times 3 gives 27 out. Plug the 0 in, of course you get 0 out. Plug the 8 in, similar analysis. Cube root of 8 is 2, square it, get 4. Multiply by 3, get 12. So we get out function values of 27, 0, and 12. The greatest, that one, is the absolute maximum. The least, that one, is the absolute minimum. Absolute maximum is 27 and occurs at theta equals negative 27. Absolute minimum is 0 and occurs at theta equals 0. And that's all they ask us to do on that one. Could you graph this using those 3 points? And the fact that we have a place where the derivative is undefined, I could probably get a moderately good idea of what the graph looks like. Just based on those 3 points and the fact that it has a place where the derivative is undefined. Maybe I'd have to borrow a little bit more algebra knowledge. This is, because of the 2 there, this is a non-negative function. It's 3 times the cube root of theta squared. The 2 squares some things. So we're dealing with a non-negative function. That might be some useful algebraic knowledge if I was trying to graph it. More of that in the future. They wanted absolute max and mins. There they are, and that's where they occur. Okay, here's one a little more interesting. Find the critical points and domain endpoints. I think it's only got one endpoint. For the function y equals f of x equals x squared square root of 3 minus x. Then find the value of the function at each of these points, the critical points and the endpoint. and identify extreme values, absolute and local. Okay. First, the domain is the interval, negative infinity to 3, including 3. You would never include the negative infinity because that's nonsense. But this is an interval. It's an infinite interval, but it does count as an interval. It's not a closed and bounded interval, so I can't use the extreme value theorem. So we may not have absolute maxes and absolute mins. I'm not guaranteed it because I don't have a closed and bounded interval. This function is continuous where it's defined, so it's continuous on its domain, but its domain is not a closed and bounded interval. The extreme value theorem does not apply. All right, extreme value theorem told you conditions under which you get absolute maxes and mins. It doesn't apply. Well, we may not get absolute maxes and mins. I think we get an absolute min and we don't get an absolute max. All right, so why is this the domain? To avoid square roots and negatives. We need 3 minus x to be greater than or equal to 0 because we're taking a square root of it. Rearrange that. That gives you x is less than or equal to 3. It gives you this in interval notation. Oh, so 3 is an endpoint of the domain. So we'll have to evaluate the function at 3. The function is non-negative. You believe that? X squared, that's non-negative, regardless of what x is. And the square root of some stuff, that's non-negative. Square roots are never negative. We've been through this. So this is a product of two non-negative things, and so is itself non-negative. Yeah, the function's non-negative. It could be 0. In fact, it's 0 when I plug in x equals 0. It's 0 when I plug in x equals 3 as well. Get the square root of 0. But the function is non-negative. The domain's not an interval of the form a, b, so we can't precisely follow the 3 steps we had. There's no left endpoint. But still, let's go through and find some critical points. This one's a bit longer of a story, really, because the domain is an unbounded interval. All right, critical points. Let's see, we've got f of x is x squared, 3 minus x to the 1/2. Let's write the square root as a 1/2. So it'll be easier to differentiate. We'll have derivative of the first. It's a product times the second, plus the first, x squared, times the derivative of the second. Bring the 1/2 down, subtract 1 from 1/2, leaving negative 1/2. Multiply by the derivative of the stuff inside. Picks up a negative here. Get a common denominator and simplify. And if you're as tired of listening to me as I am of talking, let me leave it to you to trace through these details. And we'll get this out as the derivative. So where is this 0 and where is this undefined? It's 0 when the numerator is 0, which occurs when x equals 0, and 12 minus 5x equals 0. That'd be what? X equals 12 over 5. Yeah, x equals 12 over 5. That's what, 2.4. It's in the domain, just checking. It is in the domain. Critical points were points in the domain. And 0 and 12 divided by 5. Those are both domain elements. So the critical points are 0 and 12/5, where the derivative is 0. Any place in the domain of the function where the derivative is undefined? Yeah, at 3. 3's in the domain. And this function, the derivative, is undefined at 3 because we get division by 0. So x equals 3 is also a critical point because f prime is not defined at x equals, sorry, I should read x equals 3. So undefined derivative at x equals 3, derivative of 0 at these other points. So we're going to draw a graph, and we need to illustrate somehow how this non-existence of the derivative affects that graph. All right, so let's check the critical points, 0, 12/5, and 3. We had the function x squared, 3 minus x square root of, plug the 0, the 12/5, and the 3 in. I had to put it in smaller fonts to get it to fit on the slide. And we get out values of 0 here, 0 there, and something that's non-zero and non-pretty. We get 144 over 25 times the square root of 3/5. So I don't know, it's positive. The numerical approximation of this, I could care less. It's positive is really all it mildly catches my eye. It's bigger than 0. So it's looking like we've got mins here and a max here. But I can't make a claim about an absolute maximum because I don't have the extreme value theorem working for me. I don't have a closed and bounded domain. Remember, f of x is greater than or equal to 0. It was x squared times the square root of something or other. So it's never negative. Well, then 0 would have to be the minimum. So since I know the function is non-negative, at x equals 0 and x equals 3, we're getting this absolute minimum of 0 out of the function. So we have an absolute minimum at x equals 0 and at x equals 3, and that minimum is 0. Probably should have added that. I'm claiming, and we got a local maximum at 12/5. This thing is a local maximum. All right, I got some explaining to do on why that's the case. I say, well, 12/5 is between 0 and 3. The function value is bigger than f of 0 and bigger than f of 3. If f had a larger value than 12/5 for something between 0 and 3, if the function got bigger than this, somewhere between 0 and 3, then we'd have a local maximum. For differentiable functions, and this is differentiable on these interior points of the domain, differentiable functions will have critical points where the derivative is 0. That's what Theorem 4.2 said. So if there was another place where the function had a local maximum other than at 12/5 between 0 and 3, we'd have another critical point where the derivative is 0, because this function is differentiable between 0 and 3. It's differentiable at 0. It's not differentiable at 3. It's got some endpoint problems at 3. But there couldn't be another value between 0 and 3 where the function gets bigger than that, or it would have been a local extremum, and we'd have a critical point, and the derivative would have told me about it. So that's the somewhat involved argument that it must be that 12/5 is the largest value of the function on the open interval from 0 to 3. So there's you an open interval where this is a local maximum. So we've got a local maximum at x equals 12/5. For fans of ugly numbers, that's the local maximum. All right. This one's involved. Let's look at the picture here. I want to talk about what happens over here in the negative realm. What happens for x less than 0? Let's see, differentiable for x less than 3. All x interior points in the domain of f, which we have local extrema, will have a derivative of 0. So we've taken care of that. That's got to be the only local extrema. What I'm getting at is there are no other local extrema over here. If there was, there'd be critical points because this is a differentiable function for x strictly less than 3, differentiable for x less than 3. If we had other extreme values, we'd have more critical points. We don't, you don't have other extreme values. So what I'm left to puzzle is, well, what's this function do over here when we take negative input values? They're in the domain of the function. We got no problem if x is less than 3. If x is a big negative number, 3 minus x is a big positive number, and we can take the square root, no problem there. The thing I need to notice is we can make f of x large and positive by making x large and negative. You put a big negative number in here, it's going to get squared, giving you a really big positive number, and then you're going to take that negative number, do a 3 minus x thing, take a square root. That'd be the square root of a big number. You're getting big numbers out. If you put big negative numbers in, you're getting big positive numbers out. That's rather informal, but it's all I got at this stage. So what you're getting out when you put these big negative numbers in, I bet it gets bigger than f of 12/5. It does, and we could find that by plugging in specific numbers. This was, geez, I might want a decimal approximation. If it wasn't big, it was on the order of 144 over 25, the square root of 3/5 or something like that. On the order of, I don't know, 3 or 4. I can make this function a lot bigger than 3 or 4. Plug in, let's see, how about -6? If I plug -6 in, we'll get 36 times 3 minus -6. That'd be the square root of 9. It'd be 3. We get 3 times 36. Just don't make me do the arithmetic. That's 144. Is that right? It's sufficiently bigger than this thing over here. It doesn't have a maximum, an absolute maximum value. And I didn't expect it necessarily to, because the extreme value theorem doesn't hold. What's the graph look like? Well, all I know is it gets big over here. And I could learn some other stuff about it, but with what I know now, I've made an argument that it gets large over here on the negative side. It passed through this point. Ooh, and remember, x equals 0 is a critical point because the derivative was 0. So put a little red line here to indicate horizontal tangent line there. Did the same thing at 12/5. There's a little horizontal line here. At 3, the derivative was undefined. So put a little vertical hash mark there. This is a pattern I'll follow. So this indicates critical points where we had horizontal tangent lines. This indicates critical points where the derivative is undefined. And there's a couple of different ways the derivative can be undefined. It could have a vertical tangent, which I think it does. It could be an endpoint of the domain, which I know it is. It could be a cusp or a corner. So maybe that's more than 2 or 3. But I'm going to put a little vertical hash mark to indicate the derivative is undefined at those kind of critical points. So what's the graph look like? Well, I know it gets big over here. I don't know that maybe doesn't level off, but I don't think it does because of the x squared. We could test it for horizontal asymptotes where you'd find it doesn't have them on the left. But I do have some vagueness on what happens over here. But I do know it's non-negative. The only place it's 0 are the 2 points we found. When we come in here, it levels off, passes through the origin, goes back up. Up here, it levels off, goes back down to here. It has to look like that. It couldn't wiggle more. Over here, it couldn't wiggle up and down. If it did, I'd have more critical points and I'd have local extrema, and we don't. The derivative told us where the extrema were by giving us the critical points. So the graph has to look, gee, I don't know, it's probably a little sloppy on this side, but it has to look largely like this. This is the general shape of this graph. We'll have ways to analyze it in more detail and how it behaves over on the left later. But for now, I'm happy with this graph. It satisfies the conditions we know. It's got absolute minimum of 0. It's got a local maximum of whatever we had for this, and no absolute maximum. Let's look at another one. Okay, I think this is the last one. It says if an even function, remember what an even function is, they absorb negative signs. If I plug in -x into the f function, I get the same thing I would get by plugging in x itself. F of -x equals f of x. The f function absorbs negative signs like a squaring function, like a raising to the 4th power function. That's why they're called even functions. Like a cosine function. A cosine function absorbs negative signs as well, property of cosines. So if we have an even function, f, has a local maximum value at x equals c, can anything be said about the value of f at -c? Give reasons. This you could analyze, and possibly even may have done this in a pre-calculus class. An even function is symmetric with respect to the y-axis. So if there's a local maximum at x equals c and we have symmetry with respect to the y-axis, I bet you there's a local maximum at x equals -c as well. That's legitimate if you interpret even functions as those which are symmetric with respect to the y-axis. Well, let's give reasons, but let's give somewhat more of calculus reasons, calculus-related reasons. First off, if C is 0, then C and negative C are 0 and negative 0. It's the same thing. We can say it's got a local maximum at negative C because negative C and C are the same, and it's got a local maximum at C itself. Just a caveat there of what happens when C equals 0. Otherwise, if C is not 0, then things get more interesting. If F has a local maximum at x equals C, which is non-zero, then by the definition of local maximum, there's an open interval I containing C where f of x is less than or equal to f of C for all x in that interval. Let's call that interval the interval from A to B, the very definition of local maximum. So that's what we're really illustrating. I want to talk about what happens at negative C. Using the fact we have an even function, which absorbs negative signs, and the fact that C is an interval, C is an element of interval I. So C must be between A and B. It says over here, interval I contains C. So C is between A and B. We're going to look at negative C, so we'll have to deal with that. Function f is hypothesized to be even. That means f of x and f of negative x are the same for all x in the domain of the function. We've got, we're going to choose an x in the interval from negative b to negative a. By writing a, b is an interval, a is less than b, so negative b is less than negative a. Introduce a negative and reverse inequalities. So take x to be any number in this open interval here. Then negative x would have to be in the interval AB, and I know things about function values related to elements of the interval AB, the interval capital I. If you like, write this as an inequality, run through with a negative sign, and it'll produce an inequality that says the same thing as this inclusion of negative x in the interval AB says. So if we first choose x in the interval negative b to negative a, well, let's rewrite that as negative x in the interval from a to b. I want to talk about this because I know things about this in terms of hypotheses. For all such x in this interval, we have f of x and f of negative x to be the same because we know we've got an even function. We know whenever we choose an element of the interval ab, like negative x, what we get out is stuff less than or equal to f of c. So I know f of these values is less than or equal to f of c. F of these values, negative x, is less than or equal to f of c. Hey, I also know, because f is an even function again, f of c and f of negative c are the same. It's just the definition of local maximum. So let's take that stuff and ignore big chunks of it. What we've shown is there's an open interval containing negative c, namely the interval negative b to negative a, right? If c is in the interval ab, negative c is in this interval. And when we choose values x from that interval, we have f of x is less than or equal to f of negative c. And we went through some intermediate stuff to claim that. So we've shown for negative c, there's an open interval containing negative c, such that when I choose anything from that interval, we have f of that anything less than or equal to f of negative c. That's the very definition of local maximum value of this function f at x equals negative c. So there's an illustration using, the calculus stuff, using really just the definition of local maximum. This was also easily explained in terms of symmetry, if you think what even function means in terms of symmetry. And that's the last one of those. So that completes this section. So what lies ahead is a bunch of use of derivatives to graphing. So we sort of scratched the surface on it with this max-min stuff. We're going to look at increasing and decreasing functions. I think that comes in the next section. And use information about that in terms of graphing. If not the next section, then the following section. So have a nice day. I will see you soon in section 4.2. Bye-bye.